Hello everybody. So in this video we're going to start with the example that we're going to try in the 4 modules of the ideal reactors in Aspen Plus. So the example that we're going to go through is a reactor that does the esterification of ethyl acetate by the reaction of acetic acid and ethyl alcohol. So it's kind of like the inorganic reaction of acid plus base equals salt and water. So this is the acid, and this is what we can call the organic base, which is the alcohol, and this is gonna give us the salt, which is the ester, and water. And the reaction is, we have some information about the reaction, like the K, which is the rate constant, and the activation energy. And we're not going to use these now because these are going to be used in the kinetic reactors. So in our case, we just need to know that it is 1 mole reacts with 1 mole to give us 1 mole and 1 mole. So this is the information that we need to know for now. And we have information about the feed conditions. The feed is 75 degrees Celsius, 1 atmosphere, composed of 11,570 kilograms per hour of acetic acid, 8,600 kilogram per hour of ethyl alcohol, and 160 kilograms of water per hour. These are the information that we know, and we need to know the or to get more, or as much information as we need or as we can from the 4 modules. What we're going to do is I'm going to go to Aspen Plus. I have already defined the 4 components just to save some time: ethanol, acetic acid, water, and ethyl acetate. The components are all polar components, and because they have the oxygen atom that can form hydrogen bonds, so we use the NRTL with the Heeren-O'Connell equation of state. Because we have carboxylic acids, and that's why we need to use this. And you can check the method assistant for more information about them. So we are ready to go to the simulation environment. And when we go to the simulation environment, we need first to define the feed. And the feed, as we said, the temperature is 75 degrees Celsius and 1 atmosphere. This was mass flow of kilogram per hour. Ethanol was 8,600. Acetic acid 11,570. And water was 160. So we have now the feed stream already fully defined. But we need to keep in mind that this feed is going to be the same for the 4 modules. So let's take a look. These are the 4 reactors that we're going to be talking about today. And these are going to have the same feed. So, and instead of making copies of this file, we can use what we have here as in the manipulators. And the manipulators, we have duplicate, we have multiplier, we have stuff like that. So it's the duplicate is kind of like the splitter, but it doesn't split. It keeps the composition and the flow rate. It duplicates the file, the stream. So I'm gonna get 4 outputs out of this. Of course, this is a hypothetical module. It's not a real module that we can use in real life. But this is easy because if I need to change anything in the feed, I just change it here, and it's gonna change automatically in the 4 streams. So I'm gonna call this the feed to the. Let's take a look at the stoichiometric reactor. This is gonna be the feed to the equilibrium reactor. This is gonna be the feed to the Gibbs reactor. Oops, we cannot put space. The feed to the Gibbs reactor, and this is gonna be the feed to yield. I'm gonna keep the yield to the end, and I'll let you know why. But we will go through the 4. Don't worry, I'm gonna pass in one of them. So I'm gonna go first with the stoichiometric reactor. And as you know, sometimes the volume, let me just call it stoichiometric reactor. Sometimes the modules are big, so you can resize them if you want. So what I'm gonna do is I'm gonna put one stream to the as a feed stream, and you can um, get the outstream out of it, and this is gonna be the product of stoichiometric reactor. And let's open it and see what information that we need to define here. So we need to define the operating conditions. We're gonna operate at the same temperature of the feed. It's gonna be 75 degrees Celsius and 1 atmosphere. So this is the first thing we need to define. You can define the temperature, you can define the vapor fraction or the duty, and it's gonna be the similar to what we used to define or to the information we give to define a stream. We defined the temperature, the vapor fraction, and the pressure. The same here, but here it adds the duty because it can calculate the temperature from the duty. So it doesn't matter. So for the reactions, we need to define the reactions that take place. And keep in mind here, we define only the stoichiometric coefficients of the reaction. It's a very, very basic definition of the reaction. We'll find here there is a reaction part here in the navigation bar. And this is gonna be for the kinetic reactions or the kinetic reactors. So you define the kinetics of the reaction. So when you define the reaction here, it's a global reaction. It is available in any other unit. But here the reaction that you define is just specific for this unit only or this block only. So you can define the reactions. First, you can define more than one reaction, but in our case we have only one reaction. So I'll define the ethanol plus acetic acid, and this is gonna give us the water and ethyl acetate. So this is I defined here the reactants, and I defined here the products. Okay, so if you put some of the reactants in the product part, it's gonna mess up everything. So you put here the coefficients of the reactions or the reactants. You know this is 1 and this is 1, and you notice that it turned the number into negative because the stoichiometric coefficients for the reactants must be negative. So if you forget the negative, it's gonna be corrected by the software. For the reaction, it's now defined, but here there is the products generation. You can define either how much moles per hour of these reactants will be coming out. So I can define, say for instance, I'll have 89, just any weird number, so that we can check it of the reactants to come out. Or you can define the conversion. So I'm gonna do this first, and then I come back and do the fractional conversion. And then I'm gonna run the file. It's now doing the basic calculations for everything, and we are waiting. So it's now generating results, and the results are available. And now let's see what kind of results that we can see. So it tells us the outlet temperature and the pressure because it's the operating temperature, the duty because it's assuming that it is isothermal reactor. So you need some energy to be put into the reaction or to be pulled out of the reaction. For the balance, it just gives you information that the number of or the mass in and out is the same, so you have the difference is 0. For the phase equilibrium, it gives you the x and y's and the k values for each one of these components. But here you can see that it gives you the reaction extent. It tells you the conversion is 87, or this is the number of moles that come out. It's 87 kilomoles per hour. Okay, and this is for reaction 1, which is the reaction that we know, and you can get the heat of reaction, but it's not generating the heat of reaction actually. And this is something that we will visit in a minute. And we can see that it can give you, from the stream results, you can see how many moles coming in and out. So of course the mass is conserved, and the number of moles is going to be the same because the reaction consumes 2 moles and produces 2 moles. So the number of moles will be always the same, but the detailed number of moles is going to be different. You have here the number of ethyl acetate moles that produces 87, and this is the difference between them. Okay, you can get them as mass flows, you can get them as mass fractions, you can have as mole fractions. It's up to you. You can get any of these. And now let's go to the setup again and see what else can we get out of it. So define the reactions. and there is something here about the combustion, but we're not going to go through this. It gives you information, or you can ask it to give information about the combustion products if it's nitrogen oxides or something like that. We're not interested in this now. And here in the reaction, this is the heat of reaction. This is the point that I want to go through, is that it does not report the calculated heat of reaction, or you can report the calculated heat of reaction. For instance, I'm gonna say that for reaction 1, I'm gonna calculate the heat of reaction with respect to whatever, ethanol. And this is important actually, because the heat of reaction comes in units of calorie or energy per mole. So it's how many joules or calories of energy are coming per reaction of 1 mole of the reactant. Of course, in our case, it's not gonna be different or make a difference if I put ethanol or put acetic acid, because it's 1 mole per 1 mole. But if it is 1 mole reacting with 4 moles, then it's gonna be different. So the energy released per 1 mole of A is gonna be 1/4 of the heat coming of reaction of 1 mole of B, because the stoichiometry is not 1-to-1. And here the reference temperature and pressure is because when you calculate the heat of reaction, you do not calculate the heat of reaction based on the actual temperature only. You have to refer to a base temperature or reference temperature. So usually the heat of reaction is calculated from the heat of formations, and the heats of formation are always available at 25 Celsius. That's why the reference temperature is always 25 Celsius. The other tabs are not kind of important now. You can have the utility. I think we talked about the utility before. Anyway, so we should be good to go. And now I'm gonna run the same run with only reporting the heat of reaction, and I'm gonna see the results. Is gonna be the same, but here you see the heat of reaction is produced. Just keep in mind one more thing, that when you do the heat of reaction, that it reports the reference phase. And it's important because in our case, the reaction is liquid phase, and this is going to change the heat of reaction. So the heat of reaction that we were calculating was positive, and positive means that it is an endothermic reaction. But this reaction, and it reported that it's endothermic reaction because the reference phase was vapor phase. But actually the reaction is coming in a liquid phase, and that's why the reference phase should be liquid phase. And that's why you see that the heat of reaction now is negative. It's negative 535, which means that it is an exothermic reaction. So it's an important thing that you need to keep in mind, is the reference temperature, pressure, and the reference state as well. Let's see the last thing about the reactions here that we reported. We need to talk about, I'm sorry, is that when you define the fractional conversion, you can ask the software to give you the fractional conversion of, and this is a fraction, so it has to be between 0 and 1. So if it's 70%, you have to put it as 0.7. Of the component, you can define any component. If I put acetic acid, it's gonna give an error, ethyl acetate, because the ethyl acetate is a product, and this is what it tells me, that you have to put a reactant. So for the reactant, I can put ethanol or acetic acid, and usually it's for the limiting reactant, and the limiting reactant is the one that is not in excess in the feed, which is the ethanol now. But you can put it in for acetic acid. It's not going to be a problem. And when you run the file, you can see the results. Again, everything for the duty, for the balance, for the phase equilibrium, it's going to be the same. The reaction, it's not different, but here you can see the reaction extent is not the same number that we put before. And before we put 87, and this was 87, but here we put the conversion, and it tells us how many moles per hour of the reactants are reacting. So this is the 70% of the feed. So when you go to the stream results, we can check the mole flows, and it's 186, and the product is 130.63. Again, for the mass flow, you can see similar things. So this is all for the stoichiometric reactor. The main output, in my point of view, the main output that you can get out of here is the heat of reaction. The heat of reaction is not easy to calculate if you're gonna calculate it by yourself, and I've already showed that before in the Microsoft Excel series. You can check it if you're interested, to see how you calculate it and how you go from the actual temperature to the reference temperature, and then from the reference temperature back to the actual temperature. So it's a tedious series of calculations. So I find it very useful to have it calculated here, and of course this is gonna be more accurate because it's not assuming ideal conditions, as we do in Microsoft Excel calculations. So this is all for the stoichiometric reactor, and I'm gonna stop now, and we will go for the next reactor in the next video, inshallah. So see you then.